In this video, we're gonna try to find the values of x for which this series will be convergent. So we see from this term here that this one looks like a geometric series. And we know that we can rewrite it like this way. The sum of x plus 3 over 4 to the power n. Okay? So, and n is going from 0 to infinity. So to make it, to make sure that it's convergent for a geometric series, we know that we need to have this condition r is less than 1 in absolute value. Okay, that's what we're gonna have here. Assume that this is our r. X plus 3 must be, x plus 3 over 4 must be less than 1. Okay, so doing some simple algebra, we have x plus 3 is between minus 4 and 4. And adding minus 3 to both sides, we get x is between minus 7 and 1. Okay, so that's the key that we get. Okay, and this gives us our result for some geometric series. So this is the only condition that we need to have this one. Another thing that we can use to check if we assume that some series is convergent, that means the general term an goes to 0 as n goes to infinity. We can use this one as a criterion for convergence or divergence, but not all the time, because this is a sufficient condition. Okay, that means if it happens, the series is convergent. Okay, but sometimes when the series is convergent, we need to have this one. Sorry, when the series is convergent, we need to have this one. But when we have this one, it doesn't mean that the series is convergent. Okay, so when the series is convergent, we need to have this condition. Okay, because sometimes like this one, this series 1 over n, our term here is a n 1 over n. So this one goes to 0 as n goes to infinity, but this one is divergent. Okay, so a good thing that we can deduce from here is that if the general term doesn't go to 0 as n goes to infinity, that means our series from some number is divergent. So this is the good thing here. So when the general term doesn't go to 0 as n goes to infinity, that means our series is divergent. Okay, we stop and without doing any work. And this is called the test for divergence. Otherwise, we have to do some work. We have to do more tests. Okay, and this will help us find the sum that we need. For instance, assume that we are trying to find the sum of this series, arctangent of 2n with n going from 1 to infinity. So here we can see that the general term here is arctangent of 2n. So when we take the limit of an, so it's the limit of arctangent at infinity, which is pi over 2. It's different from 0. Therefore, we can deduce here that our series is divergent. So because of this condition, this test, okay? So this test let us see if the series is convergent or divergent. So this is basically for divergence. Okay, if the general term is different from 0, As n goes to infinity, that means the series is divergent. Okay? For instance, we can get one more series here. This series, n plus 1 as n goes from 0 to infinity. Is this one convergent or divergent? This is, let me say, an is n over n plus 1. So when we take the limit here, and as n goes to infinity, an will reach 1. The limit will get to 1. That means an is different from 0 as we take the limit. Therefore, this series is divergent. So this is the usefulness of this test of divergence. Okay. Other thing that we can use is that sometimes the limit is not easy to evaluate. Okay, it's not easy to see, or it requires more work. Okay, that's why you have other tests. But it's good to know this one. Sometimes before you start your study, check if the general term of the sequence or of the series doesn't go to 0 as n goes to infinity, and you stop. You can say for sure that your series is divergent. Otherwise, we're going to use more tests. And if we have a general formula for or an easy formula for the partial sum, let's say the partial sums is the sum of the first, let's go from 1 to n, the sum of the first n terms of the sequence or of the series. So this is a1 plus a2 plus an. Okay, we collect n of them, and we take the limit. Okay, and we take the limit to infinity to see the behavior of the series. Okay, sometimes we have this one is easy to compute, sometimes it's not, and we just check whether it's convergent or divergent. I think one thing that we can learn is that if this series, when we take the limit as n goes to infinity, so it equals some s, it's convergent, then this term an has to go to 0 as n goes to infinity. If an doesn't go to 0 as n goes to infinity, then our series is divergent. And you can check these examples like 1 over n, okay? And remember this one. This is a counter example for this one. And some other ones like the exponential of n. Let's have this series. This is the divergent one. Why? Because e to the power n goes to infinity. It doesn't go to 0. Okay? So the limit goes to infinity. It doesn't go to 0. It's different from 0. Therefore, this series is divergent.